Right. Okay. So we are doing stationary waves. Now, Ali did progressive waves the other day. So what do you know about progressive waves? Well, they are a wave moving energy from one place to another, from a source to a detector. They occur when a medium is perturbed, oscillates somehow, and the energy goes from the source to the detector, but the medium does not move in the direction of the wave much. Okay, so yes, you got your longitudinal wave, but when you have a loudspeaker on one side of the classroom and your ear on the other, the air doesn't actually rush from the loudspeaker to your ear. Each air particle vibrates a little bit, even though the sound wave is moving right across the room. So that's an important thing to know about progressive waves. And then I'm guessing you did the V equals F lambda formula for that, and you flogged that to death. I'm sure that's what you did. Well, what we're going to do now is something called a stationary wave. Now, some examples also call it a standing wave. I'll show you the different chunks of the specifications which you really need to know. So OCR call it a station. No, they don't, you see. They say it's a stationary wave, or in brackets, they call it a standing wave as well. And then in part one, they call them stationary waves. That's not very helpful. So in their questions, they might call them both stationary waves and standing waves. AQA, on the other hand, no messing about, they are stationary waves. And EdXL also say standing / stationary waves. So you've got to take your pick. So if you see standing wave or stationary wave, you know that it is the same thing. Right. Then you've looked away. So there is a classic wave. Now, what I've done is I've just taken the most beautiful sine wave I could draw, using Excel, by the way, and plonked that on an oscilloscope grid. So I'm going to say that is a wave which is moving from the left to the right, as you've seen with progressive waves. So that is a progressive wave. Now, due to magic, due to something, we shall find out what in a bit, there is an identical wave which is passing the other way. So the black wave is going from the right to the left. The red wave is going from the left to the right. They are passing in the same medium. They are identical waves with the same amplitude, the same wavelength, the same frequency, same velocity. The red one is going to the right. The blue one, or the black one, is going to the left. Now, if that happens, then the most gorgeous maths falls out. We don't have to do that, but I'll show you what happens. But let me say this again, because this is the condition for a standing wave. It's when you have two identical waves passing through the same medium in opposite directions. Okay, that is what we're going to have, and that creates what's called a standing wave. So I'm going to show you one of my favorite animations by this Walter Fed guy. And so this is a still from it. Now let's just tell me what we are going to look at. So the most important thing is the first one is the wave. So the red wave is going to be going that way. Okay. The black blobs represent the medium. When the wave goes past, the black blobs are perturbed, they are moved, they are displaced from their mid positions. That's really important. So when we watch this, watch what happens to the black parts of the medium as the wave goes through. Now, the easiest wave to look at is a water wave, or a wave on a string, or a wave on a stretched wire. More of that later. Okay, what I'm going to do is get this little animation up and show you what we are going to do with it. Here it is. So let me have a look. Why doesn't it show the black blobs? I don't know. Doesn't really matter. The black blobs aren't there. Now, if I click resume, I can make it go. There it is. So there's our beautiful red wave traveling through the medium from left to right. Okay. I'm going to now click single steps, and I'm just going to go through ka-chunk, 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 so I can pause it when I want to show you something interesting. So I'm just going to carry on with this wave. There it is. It hits that wall, and that's it. Okay, so the energy is absorbed. That's it. Nothing happens. That is, I'm going to animate this. So there it goes. So that is our incident ray going from left to right. Now, what happens at that vertical line, the boundary, is the wave is reflected. So it's going to be reflected from the right to the left. So now, if I pause that and get rid of that and show the reflected wave, this is what the reflected wave is doing. It is going the other way. It's being reflected. I'm not going to say like yet, because we're going to see examples of these. Okay. Now, the interesting thing is what happens when I have both waves at the same time. So I'm going to click incident wave, incidenting wave. I'm going to click the incident wave, the red one going to the right, and the reflected wave going to the left. Now, that is what's happening in the medium. Both waves, they are identical waves passing in the same medium in opposite directions. Now, something weird happens. Something weird happens. I'm going to try to pause it when they are, I don't have to do that. I'm going to go in single steps. And now I'm going to go bop, 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 bop. There we go. So now we've got the red wave and the blue wave are like that. Okay. Now, if you remember your superposition, or you don't have to because it's common sense, I'm now going to draw this on my little screen thing. I'm going to draw in green, I'm going to draw that point there, because at that point, the red wave is 0 and the blue wave is 0. So when they add up, 0 plus 0 is 0. Okay? I'm going to do the same for that point there. The red wave is maximum on my screen 3 centimeters. The blue wave is maximum on my screen 3 centimeters, which means that the apparent wave, when you add them together, is up there. Okay? So I'm now going to do where all of the waves are 0, 0, 0, 0, 0, like that. I'm going to do that. And when they are there, I'm going to do that. When they're there, I'm going to do that. When there, I'm going to do that. There, they do that. And there, they do that. So if I were to put those two waves together and show you what the resultant wave is, that's it. Okay, so the resultant wave with the black blobs on is what you get when you have the red wave and the blue wave combined in that medium. Okay, now watch what happens when let me get rid of my little dots, because you can see what's going on there. Let me get rid of my little marks. So now let me show you what happens when we have, I'm going to animate this, when it carries on moving like that. The blue wave to the left, the red wave to the right, and the black one is adding up each point as it goes. As the red wave goes through the blue wave, the black wave is the resultant wave. Now, what you can see, much to your surprise, I know, I can tell, what you can see is it's not moving. The peaks don't move left nor right. The bits where it's 0 do not move left or right. What's happening is it's just flapping up and down, but it is not moving left or right. It is standing still. It is stationary. That is a stationary wave. Okay, let me just pause it at any time. There. Okay, so what I'm going to do is show you how that actually happens. So when you can do this, you can stop it wherever you like. Now, what I'm going to do is to take that point there on the blue wave and that point there on the red wave. You know why I did that? You know, because the blue wave is the same distance above as the red wave is below, because maths says so. So if you add the same above to the same below, you get 0. You get that. It is not moving at that point. So if I now start to animate this again, Okay, if I start to animate it at any place where you, not slow motion, it's ridiculously so, where you see that N letter, the red wave is the same distance above as the blue wave is below. Always. That means the resultant is 0. It's not moving. Okay, and likewise, when you see it now, that's when the two waves are adding together and you get a maximum. You get either a maximum above or a maximum below. That is called a standing wave. Now, I think you know that the ends where the thing is not moving, those are called nodes. So where the medium is not moving, that is called a node. And where the medium is moving greatest, that is called an antinode. I don't think it comes clearer than that. Okay, I'm assuming that's okay. Okay, that is what a standing wave is. Now that you understand that, I'm hoping, because if you don't, I'm waiting for something in the chat. So now that you understand that, what I'm going to do is to show you examples of standing waves and really labour a point because the exam board ask you about a certain range of examples. So here is one. A microwave transmitter is sending a pulse of microwaves towards a metal plate. What is it doing? Then it is reflecting it back. There you have the conditions for a standing wave. So I'm going to draw a standing wave because that's what every single question on this thing does. So first I'm going to draw. Go on. Oh, no, it doesn't do it. First, I'm going to draw a straight line, which is going from there to there. That's it. Pardon me. So that is the direction that the wave is going. Now I'm going to draw my standing wave. So you draw it like this, just like we had before. Ba-bum, 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 ba-bum. Like that. And then it says, I bet you it'll say, label the nodes with an N and the antinodes with an A like that. Okay, that's the bog standard. Okay, I'll show you many examples until you get bored. The next one is, oh, look, a loudspeaker hitting a metal plate. So the loudspeaker produces the sound waves. The sound waves go towards the metal plate. They are reflected from the metal plate and you get standing waves because you have the wave and the other wave through the same medium. They're coming from the same source, so they have the same frequency, roughly the same amplitude, but not quite. But we're going to botch it. So you get a standing wave. Now, what the microphone does, it picks up the amplitude, the loudness of the sound, so you can work out roughly by measuring the height of the oscilloscope trace how loud the sound is. And much to your surprise, when you move the microphone in this direction, like that, sometimes the amplitude of that thing is a maximum, where it's loudest, where the air is flapping around most, that is an antinode, and where they cancel out always, it's a lot quieter and you get a node. Okay, let's have a look at another example. Maybe you have got yourselves your microwave ovens. In your microwave oven, you have something called a magneton, which produces the microwaves. Now, those microwaves go through waveguides and are sprayed into the cavity of your microwave oven. They travel into the oven. The oven has got an oven wall, which is metal. The microwaves are reflected from the oven wall and bounce back and go through each other. That is the condition for standing waves. Now, a microwave oven is a slightly peculiar shape, and it's got, so there are lots of reflections going on, and you do get these nodes and antinodes in a microwave oven, but you want your food to be cooked uniformly. So you put it on a turntable, so the turntable moves the food through nodes and antinodes to make sure that it is cooked. evenly throughout. So that is how you get standing waves inside a microwave oven. But if you take the turntable out and lay a bunch of marshmallows in there, so you get a tray, microwave safe tray, and you put marshmallows on and then turn it on so the marshmallows do not move, then you get your marshmallows looking like that, and kind of in a regular place you get the marshmallows melting. They melt a lot in some places and not much in others. And this question was asking you about the wavelength of the microwaves, and then knowing the velocity of the microwaves, they ask you to find out the frequency of the microwaves. But we'll do that question in a bit. We'll do that in a bit. Okay, this one. This is the one that you are going to do for your CPAP. It is where you have to investigate the oscillation of a stretched wire. Okay, there are an infinite number of diagrams on this. So this one, you have got a wire. You keep it under tension by dangling a mass over the end, T equals mg. You then somehow find the frequency of the wire between those triangular blocks. So that is where the wire is twanged, or something makes the wire vibrate, and you can find out the frequency of the wire, which has got something to do with length x. Okay, and they've drawn there between the triangles, you can see a standing wave. You've got a node at one end and a node at the other end, because where the wire is pressed against the triangular prism, it's not going to vibrate. So that is a node. In the middle, where you go doing like that and twang it, that is where it's vibrating most. That is an antinode. Okay. Another way of doing it is like this. You have, as before, you have your mass, you have your bridges, which you can move to change the length between them. But to make the wire vibrate, to look at the frequency, you can use a little bit of electromagnetism, something like that, and you can put a magnetic field across the wire. So the wire is going through the magnets in north and south. The magnetic field is going that way. The wire is going that way like that. Okay? Oh, lady who's just turned up. Hello. We're just talking about standing waves and how we can get them on a wire, a classic experiment. So if you like, if you miss something, you don't understand it, then stay around at the end and I can go back because you only just logged on. Okay, so you missed a bit. I can go back and do it again if you like. So if the wire is going towards you like that and the magnetic field is like that, if you put a current through it, then you get your little field current, say, you get your left hand and the wire is moved down like that. But if you have an alternating current, the wire goes down, it goes up, the wire vibrates up and down like that at a frequency that you can control by your signal generator. So you can choose what frequency you are going to make the wire vibrate at, and then by either adjusting the length of the wire or the mass, you can make it produce this gorgeous standing wave. Okay, so this question, I didn't like it. I didn't like it because why have they shown on the oscilloscope a weirdo trace like that? What you would hope to get on your oscilloscope is a trace like that, because that is an AC supply, which makes a wire move up and down. I have no idea why they did that, because that wouldn't be particularly beautiful for your vibrating wire. Anyway, this question then showed you weirdly the oscilloscope, and I just put in here to show you that some questions surprise you and ask you about different parts of physics that you aren't prepared for. So all of a sudden they say, there's the oscilloscope trace, there's the time base, can you please work out the frequency? So that's a different part of the specification where you have to use an oscilloscope and know what the time base is for. I'm not going to do that. I'm not going to do that. You can do that. Okay, let's get back to our vibrating wire. So here is another one where you can see something quite interesting is happening. We have got a node there, a node there, and a node there. Okay, I'm only interested in those three nodes because I'm going to draw on here the wave at any instant, So I'm going to draw it when it is like that. When the string, is it string? Is it a wire? I don't know. When the string or wire is in that orientation. Okay, what it's going to do, as you saw in the animation, it's going to go flat, then it's going to go below and above. Those nodes stay there, but at any instant, it could look like that. Okay, maybe it could look like that. Oops, that. Sometimes it could look only a little bit up and a little bit down like that, but it doesn't matter because whenever it's doing it, the middle bit, that bit is still a node. Now, have you noticed what I have drawn there? I have drawn a complete wavelength. That is one wavelength. That is lambda. Okay? Can you please count the nodes? The distance between nodes is that. So there's a node, there's a node. That is the distance between nodes. Can you see a relationship between the wavelength and the distance between the nodes? Well, what a patronizing question is. Of course you can. The wavelength is twice the distance between nodes, or twice the distance between antinodes. Okay, that you need to know. You need to know that a lot because this is where your different specifications do tend to differ considerably. Right. That is a wire. I'll tell you why in a bit. That is a wire or a string. Node, node. It's a violin string. It's a guitar string. It's a string on a bass or any stringed instrument. If you play a stringed instrument, you know all about standing waves because that's what you're doing. So you've got your two nodes. So your guitar ends of the string are nodes. The wire, the string does not vibrate at the nodes. The ends are nodes because the wire is fixed. Then what you do is you take your string or wire, whatever, you move it out of the way a bit, and then you're boing like that, and it twangs. And what it does, it forms a standing wave like that. Now, that is the simplest wave that you can get. Okay, now there's a lot of confusion about what you're going to call that. It is the simplest wave. It's got two nodes and one antinode. Doesn't get simpler than that. Now, as I said before, the wavelength is there twice the distance between nodes. They've done it the other way. Half the wavelength is twice the distance between the nodes. Oh, there, they've done it there. Okay, so they've rearranged it. So the wavelength is twice the distance between the nodes. It's twice the length of this string. That is the easiest way that the string can vibrate. Now, this is what your exam boards say about it. So, OCR call that the fundamental mode of vibration. It's fundamental. It doesn't get easier than that. It is the most fundamental way that that string can vibrate. Then in brackets, they put first harmonic. Just to confuse you. AQA say, stationary waves on strings be described in terms of harmonics. Brilliant. The terms fundamental or first harmonic and overtone will not be used. So AQA use something completely different. They're going to talk about harmonics. So that OCR is the fundamental or the first harmonic. AQA, that is the first harmonic. They're not going to call it fundamental. Okay? And then EdXL couldn't care less what they call it. Okay, they'll just draw a diagram or something like that. But those two, OCR and AQA, are a little bit strange. But you've got to know which one you're doing. And obviously, when you do questions on these, you will know exactly what you are talking about. But keep your eye on that. So let's go back to our first harmonic or our fundamental, whichever one you like to call it. Now let's put a node in the middle. So now what we get is another standing wave that satisfies our criterion. The ends must be nodes. The first fundamental one has got no nodes in the middle. The next one has got one node in the middle. And it goes on, and you can work out what's going to happen next. So if you play the guitar, what you can do is you can be doing like that on the open string and you get a nice note. Then if you touch the string halfway along, and it's got to be halfway along, and then twang it, ding, it goes up an octave. Okay, because you are making the string vibrate in that mode. Okay, that is called the second harmonic. The top one, n equals 1, is the first harmonic. N equals 2 is the second harmonic. And you get the third harmonic. And on the right, you can see the relationship between the node distance and the wavelength. Okay, so the more nodes you put in there, the smaller the wavelength. And you've guessed it, there's another one, which is the fourth harmonic, like that. And it goes up and up and up and up and up. Okay, so that is what the harmonics are and how they are labeled. Sometimes a question would say, here is our string vibrating in the first harmonic. Draw the string vibrating in the third harmonic. So you've just got to remember what goes on there. So the third one has got two nodes in the middle. The first one, 0, second harmonic 1, third harmonic 2, fourth harmonic 3. Okay, so you've got to know how that works. It's a nice multiple choice question, I would think. Right, those are the harmonics. Now let's get back to, let's get back to this thing that we looked at before. So there is our vibrating string or wire, which you are going to do. You're going to do this. You're definitely going to do this. There is a formula which links the velocity to the tension on that string and kind of how thick the string is. Because if you imagine a guitar, you can change the tension by the pegs at the end. You change tension, you can tune it by changing the tension. That's what they do. Or if you look at the guitar, you can see that the highest string, top E, looks pretty thin. And then as you go down the strings, the next two, made out of the same stuff, nylon, but they are thicker. And then you get 3 metal wire round ones around the sort of fibers of nylon, but they get thicker. So the lower the note, the thicker the wire. So if we look at the top three made out of nylon, the highest is thin, then the medium one is thick, and then the biggest one is thicker of the top 3. What is happening is something is changing in that wire. Now, you could say it is the thickness. You would be right. But this formula doesn't use the thickness. It uses that. That symbol there, mu, is the mass per unit length. In other words, it is the mass of 1 meter of the string. So if you cut a meter of it and measured its mass, that is mu, the mass per meter. And it's called mass per unit length, measured in kilograms per meter. Kilograms per meter, mass per meter cubed. Now, AQA also, and in other questions on other examples, maybe they give more. I should have checked the formula booklet, but they give that formula. F, the frequency is 1/2L times T over mu for the first harmonic. So if we went back to that other one where you've got the one thing like that, that is the first harmonic, and that formula works for it. Okay, F equals 1/2L root T over mu. Now, I think that question, that formula is asking for it. That's asking for it. We could do either one, but I'm going to do the second one because it's slightly harder. Now, let me just show you what OCR say. So if you're doing OCR, this is your spec. We've got the SI units, System International. Now, they are great. Mass, length, time. current, temperature, and mole, amount of substance. Right. I'm not all that bothered at the moment about current, temperature, and the mole, because those we can leave out for another subject. I'm only interested in mass, length, and time. Mass, length, and time. Kilograms, meters, and seconds. Those are called SI base units. Okay, now what OCR would like you to do is know about all the units of all the quantities in the specification, obviously, but be able to mess about with them. So you can first of all derive different units. So for momentum, which is mass times velocity, so mass times velocity, if you know the formula, then you can get the units, the base units, kilograms, meters, and seconds. Or you can, there's density, kilograms per meter cubed. But this is the beauty. This is a nice one that OCR have hidden away. They say checking the homogeneity of physical equations using SI base units. Now, that formula that we have just seen is a beautiful one for checking the homogeneity of physical equations. And what that means is, that one. When did you do that? I think it's that one. Okay. I think that might be the one we could. I'll tell you why. I'll tell you why. Because we're going to do it again. Because we're doing it again. So here is the first harmonic equation over here. And what I'm going to do, just because I think it's asking for it, that is asking for a question. That is asking for a question. Here is a formula for the first harmonic. Show that it is homogeneous, or it is base unit homogeneous, or something like that. I'm not quite sure how they would word it. Now, what they mean by that is homogeneous means it's the same, I think. Well, that's what it means in this example, I think. Not very good English. What it means is the units on the left-hand side are equal to the units on the right. It must do. If they don't, then the equation is wrong. It's just rubbish. So let's try it. F equals 1 over 2L root T upon mu, like that. So I'm going to look at the left-hand side first of all. Now, the left-hand side, F, we know that is frequency, which is in waves per second, beats per second, something per second, I don't care, per second. So that is in per second, like that. Mu is mass per unit length, that's it. Yes, it is. Mu is mass per unit length. So if you take 1 meter of the wire and you find its mass, that is mu, the mass per meter, mass per unit length. So let's now slog through the right-hand side, and we should get seconds. Now, looking at that, it's not obvious where it comes from, but let's go through it step by step. So 1 is a number, it doesn't have any units. 2 is a number, it does not have any units. Pi is a number, no units. E, a number, no units. L, though, has got a unit, it's the meter, but it's on the bottom, so it's meters to the -1. Right, now I'm going to go through the stuff in the bracket. T is tension. Now, tension is not a base unit. We've got to turn that into base unit. Tension is a force. Force is defined as mass times acceleration. Got it. So tension is mass times acceleration, mass times acceleration. So there are the units of mass and the units of acceleration. So that's T. Mass per unit length. I hope this works. This isn't looking good. Mass per unit length is on the bottom. So U, mu, is mass per unit length. But because it's on the bottom underneath T, we change the signs. So it becomes kilograms to the -1, meters. Yes. Okay. So now we've got what's in the bracket, but it's a square root. So that is to the half. Much to my absolute delight, the kilograms cancel out. And in the brackets, we get meters times meters is meters squared, seconds to the minus 2. That's what we've got left. Now, this is what they mean by check the homogeneity of equations. You're going to have to do this for every equation. In fact, just for fun, go through your equations and see if you can show that the left-hand side equals the right-hand side. The Suvat equations are the ones they tend to choose. Sometimes the electrical ones, if they're not feeling nice, don't forget that a volt is a joule per coulomb. The joule, force times distance, there's force, distance is in meters. Anyway, let's finish this off. So that is meters to the minus 1. So if we're going to do the square root, we get meters seconds to the minus 1. Deep side, because it's worked, meters to minus 1, cancel out. We are left simply with per second, which is the same on both sides. Then we can say this equation is homogeneous. Units are homogeneous. Homogeneous. So I've told you I can't even say the word. The units are homogeneous. It doesn't mean the equation is correct. The equation should have been something like, let me just put one in. Where's my pen gone? I want to change back to brown. It could be something like pi cubed over e or something like that. These constants do sneak in there and they are unitless. So that even though the equation might be right and it is still homogeneous, no, even though it's homogeneous, it is not right. So I just put those in just to show you what I meant. So it's good. I'm happy. We can move on after all of that. Here's a question. Okay, so that is one where you simply read it, you go, oh, what's the equation? You go to your formula booklet, there it is, you write it down and you put the numbers in. We've got T, the tension, we've got the frequency F, we've got the mass per unit length, and we just need to calculate L. So it's simply a matter of put the numbers in and find out what the value is for your length of the string. Notice that the mass per unit length is going to be quite small. If you cut a meter of wire, it's going to be a gram, 5 grams or something. So this one is, it's 18 grams. Okay, but it's not a lot. Oh, it's a piano string. If you ever looked inside a piano, the strings can be quite thick. There you go. So that's just formula, put them into the formula. Let's get back to our diagram here. Oh, there you go. So the first thing is to draw the fundamental, the first harmonic. You can do that. Okay. Then I thought of something. Multiple choice question. What is the phase difference between those points? X, Y, and Z, but I cut it off. What's happening is, if you remember that animation I showed you, all of this part of the wave here, all of that wave is going down, and all of that wave is going up, which means that all of that is pi radians out of phase with all of that. It doesn't matter where it is along the wave. One part of the wave is going up as the other is going down. Okay, that is pi radians. Okay, wavelength, as I said, is twice the node separation. So that just came to me as I was staring at that diagram. Okay, so back to this thing here. You have to draw that. Right. We're going to come back to that in a bit, and we're going to look at air in tubes. Oh, my phone just packed up. Right. Before we do that, here's another question about a standing wave on a rope. So have a little read of that. Okay. Now, what questions usually say are a light string, which means that the string does not have any mass. This one clearly has mass. So if it's 65 meters long and it has a mass of 12 kilograms, you can work out the mass per unit length, which is 12 divided by 65, and you get about 0.2, job done. Easy. When it says show that it is about, you've got to do it to one more significant figures than they say. So do it to two significant figures and then say by one, no, you don't. For 1 mark, you'll just get away with it. But if it's worth more than 1 mark, you should show it to be whatever it is, excuse me a second, to more, oops. Oh man, what happened then? Oh man. Sorry, I just pulled the power supply to my monitor. So what's per unit length? So 65 divided by 12 is no mass per unit length. Sorry, 12 divided by 65, oops, is 0.18. So I would write, if it was worth more than 1 mark, I would write 0.18, which is 0.2 to 1 decimal place. That's what they want. When sometimes they specify that in the mark scheme, you've got to do it to one more significant figure than they ask, then you can round it. Right, so here is our rope. Now they've given us a clue that the rope has mass per unit length. So there's a basket dangling at the bottom. So what the man does, he flaps it around to produce a standing wave. Explain how a standing wave can be formed. Wave travels up the rope, hits the fixed support at the end, it's reflected back. You have two identical waves passing through the same medium. Then they will interfere with each other and you get a standing wave. So that's that job done. How many marks? I don't know. Right. Then, weirdly, it does this. Okay, so marking the node and antinode, I'm not going to patronize you, but how can you tell that the speed of the wave increases as the wave travels up the rope? Well, you can see that because the wavelength increases. And if the wavelength increases, V equals F lambda. If the wavelength increases, the velocity increases. But simply by looking at it, you would say that because the wavelength increases. Then it goes on to say this. Now what you can say is, if that is happening, then because the string, the rope, has got a mass, and there is a mass at the bottom, the tension must be changing. So the tension at the top there, at the top, it's holding up all of the rope and the basket. That's a lot of tension, whereas here, it's only holding up the basket. So what did this weigh? Was it 12? Did it have a mass of 12? I've forgotten. 12. Is it 12? Is it 12? It is 12 kilograms. So at the bottom, it is supporting just the mass of that. At the top, the tension is the mass of that plus 12. So as you go up the wire, up the rope, the tension increases. If the tension increases and the mass per unit length stays the same, that means that the velocity must be increasing. Okay, quite a tricky question, that. Okay, so that I think has flogged. Let me see what the time is. My phone's backed up. Oh, 12 minutes. So that is what a wave on a string looks like. Wave on a wire, a standing wave on a string or on a wire. But your OCR board have also asked you to look at waves in pipes. Waves in pipes. Now, for this, what happens is we are going to have a look at this animation here, which shows you exactly what's happening. Right. So let me just leave that to go through a few cycles. We have got a pipe can I draw on here at the same time? We have got a pipe which is open. So this is my pipe, like that. It is open at one end, the right-hand end, and closed at the other. So that could be something like a flute. A flute is closed at one end and open at the other. And by blowing across a hole, you can make the air vibrate. And then you can change all sorts of things by twiddling around with the holes in it. But let's not bother about that. Let's just keep it as simple as we possibly can. It is a sealed pipe, and it has got the fundamental vibration. That's the one you've got to know, the fundamental vibration. Now, those black blobs represent air particles. Now, at the left-hand side, the air particles are pressed up against the closed end of the pipe. That means that they cannot move. There's no movement there. It must be a node. And then at the other end where it's open, that is where the air can flap around as much as it wants. That is going to be the antinode. So the simplest fundamental mode you can get is that one, where you've got one node at one end and an antinode at the other. Not like the string where you've got a node at both ends. This one has got an antinode at the end because the air can vibrate. So that's what it's looking like. Now, they've given us two graphs. The first one is the displacement of the particles. So the left-hand side, they're not displacing at all. That's where N the node is. And at the other end, you have the antinode, and you can see that it is the displacement can be a maximum. The second one, which is a lovely multiple choice type thing, is what the average pressure is going to look like as the air vibrates. So over one cycle, have a look at the closed end. There, the particles are as close together as they can get. Therefore, the pressure is higher. And then, hold on a minute, when we get to, I can pause this. Can I pause this? No, I can't. There, the particles are as spread out. They're as rarefied as you can get. So the pressure is changing at the left-hand end. That's why the graph looks like that. But at the other end, have a look at the spacing of the particles at the other end. They don't change. They stay that. They don't change at all. So at the node, the pressure stays the same. Okay? That's the OCR thing. There is though, an experiment that you have to do which looks at that resonance of air. Okay? It's called the resonance tube. Now, let me just draw the standing waves for the three different modes. So the first one has got a node at the end and an antinode at the other. So it looks like that. That's the easiest one you can do. Then the next one up is going to have one node in the middle, slightly tricky to draw. And then you have an antinode at the end like that. Ba-boom, ba-boom, ba-boom. And then the next one, you have two nodes in the middle, and it goes, that's, but never mind, you get it. Now, if the pipe has got a length L, then I've only drawn a quarter of the wavelength in there. So lambda equals 4L. For the next one, I've only got 3/4 of the wavelength in L. And for this one, I've got 5/4 of the wavelength in L. So that's lambda 1, lambda 2, lambda 3. Obviously, the wavelength is changing. So I can change that to say 3 lambda 2 equals 4L. This one I can say 5 lambda 2 equals 4L. So we are getting a pattern. Okay? That is as difficult as this one gets. Okay? You have an antinode at the open end and a node at the closed end. Oh, hold on a minute. Hold on, have I had a message? Have I had a message? No, I haven't. Right. Now, if we take this one stage further and look at open pipes, well, for an open pipe, you wouldn't be surprised to find that there is an antinode at both ends and a node in the middle. That, I'm sure, is as difficult as OCR is going to get when it says open and closed pipes. Okay, that is what happens with an open pipe. Where it's open, you must get an antinode. And for it to form a standing wave in there at all, you've got to have a node somewhere, and there is one node in the middle. I'm sure that they won't ask you any harmonics to do with those. That's as difficult as OCR gets for an open pipe. Okay, now let's have a look at our little equation. Let's have a look at our little equation and our little experiment. So here we go. We're going to look at this thing called a resonance tube. This is the experiment that you'll do. You will set up a standing wave in the tube. Now I've drawn a bog standard pipe on the left. So I'm going to draw my simplest standing wave in there. Now I can get that by putting some water in my measuring cylinder, and then I can get my standing wave inside my measuring cylinder like that. Now the way I do that is either I hold a tuning fork over it like that, and go doing on the tuning fork and hold it above the tube, and it's obvious when it resonates, or I could take a loudspeaker which is connected to a signal generator, and I could fiddle around and find my own frequency and hold that across. Now, this is what happens. If you use a tuning fork, you can't hear them very well. So if I go doing like that, it goes, you can't hear it very well. Now, if you hold it over a tube and it so happens that you have adjusted the length of air in that tube to vibrate at the same frequency as your tuning fork, then it resonates and it goes like this. Instead of going, it goes, and you can hear it. It goes so much louder. It's like, whoa, that's incredible. It has resonated. Or if you put your loudspeaker over the top and then you adjust the frequency, it goes like that. Sometimes it goes, and it's when it gets so much louder, the air is resonating, and you know that you have matched the length of the tube, which gives you the wavelength, V equals F lambda. So you've got your wavelength, your frequency comes from here, your frequency generator, and then you can find the velocity of sound. That is what we're trying to find when we do this. Okay, so this is what the actual equipment looks like. You have a length of glass tube and you put it in a bigger tube with water in it. So it's easy to move it up and down. So what you are doing when you move it up and down, I've just noticed something awful. You are changing the length. Why is that like that? I don't know. You are changing the length of air in that glass tube. So it's very easy to do that. You don't have to pour a little bit more in, pour some out, pour some in, pour it out. You can just raise and lower the glass tube in this bigger tube of water so that you can adjust the length from the top to, would you believe it, the water surface, not a bit below. I don't know why they did that. Now, we are going to quickly, because I've run out of time. I know what I'm going to do, if it's okay with you, because this is such an important experiment, and I'll show you the CPACing stuff, I'm going to do this on Monday because, let me just show you where we are in my little PowerPoint. I am at about slide 36. Okay, if I quickly flick through, you can see that there are some more important slides that I would like to go through. So I don't want to rush through. So I got to about 36, 37. I want to show you some results. I want to show you some errors. I want to show you a graph. I want to plot a graph. I want to put error bars on, and I want to find the gradient to find the speed of sound. Now, I can't do that in 1 minute. So I'm going to stop there, and I'm going to come back to that on Monday. And in the catch-up, I'm going to spend about 15 minutes going through that experiment.